This is Logic and Computer Design Fundamental class, and today we will discuss Chapter 4, which is the combinational functions and circuits. We will go through the following points: functions and functional blocks, rudimentary logic functions, decoding using decoder, and after we describe the decoders, we will discuss implementing combinational functions using decoders and OR gates. Also, we will discuss encoding using the encoder, selecting using multiplexers. And after we explain the multiplexer, we will try also to implement combinational functions using multiplexer and inverter. And at the end, we will discuss programmable logic array. The functions considered are those found to be very useful in design. Corresponding to each of the function is a combinational circuit implementation that we are going to choose to call it a functional block. In the past, many functional blocks were implemented as part of SSI or MSI or LSI. Nowadays, they are called VLSI. The rudimentary logic functions are functions of a single variable, x, that we are going to explain in this slide. There are three different functions that are possible: either value fixing at 0 or at 1. If you fix the value of the function f at 0, it means that you are connecting this line to the ground. If you fix it at 1, it's like you are connecting this line to VCC or VDD. The other type is transferring. So you transfer 0 to 0 and 1 to 1. And as you can see in this table, the value fixing, no matter what the value of x is, if the function is equal to 0, it's going to be always 0. If it is equal to 1, it's going to be always 1. While in the transferring, the function f will be equal to x. If it is 0, you transfer it to 0 in the output. If the input is 1, you also transfer it to the output to be 1. And this is what we see here. The output will be equal to the value of x. So it will pass to the output. And you can see it's only a symbol line. The last function is inverting. So you flip 0 to 1 or 1 to 0. And we know that this is the NOT gate, or simply we say the function f is equal to x bar. So if x is 0, then the function f is going to be 1. If it is 1, then the function will be 0. These are the rudimentary logic functions. If you want to extend this idea to multiple bit rudimentary function, then you can consider a white line that is used to represent a bus. And this bus is a vector signal. So if you have, suppose that you have F0, F1, F2, and F3, F0 having the value of A, F1 is 0, F2 is 1, and F3 is A bar. You can combine those 4 lines indexed by 0, 1, 2, 3 to one thick bus that's drawn like this, and you indicate in the line that it has 4 input bundled in this line by writing /4. So now F is equal to F0, F1, F2, and F3 bundled together in a bus. We call this simply a bus with 4 lines. Also, sets of bits can be split from the bus as shown in C here. So you have this bus with 4 lines. You can take 2 lines from these 4 and you have to indicate which lines are they. Because you are already indexing them here, you know they are 1 and 2. So you take those 2 lines over here. The sets of bits need not be continuous, as shown in D. So as you can see, we took 3 lines. Those lines are 0, 1, and 3. So we skipped something in the middle, which is the index number or the line number 2. As an example, this is a lecture hall lighting control using value fixing. And you will notice that we are applying many of the things that we discussed before. So let's consider P, which is podium, and R, which represent rear. There are 2 switches in different position of a lecture hall. And let's consider that H is the light to be controlled by P and R. We will also assume 3 different mode of lights. Mi, where I is equal to 1, 2, 3. If it is M0, this means that either switch P or R can turn the house light on and off. If it is M1, only the podium can do that. If it is M2, only the rear can do that. So we will define 4 different mode control signals, which is indicated by I, capital of I, and this small I is going to be either 1, 2, 3, or 4. The truth table could be described as follows. As it follows here, the function implemented by value fixing, you would say we have P and R switches, and we try to fill the truth table by 0, 1, 0, 1, 0, 0, 1, 1, this way. The first mode, as we described, it's gonna, in this mode, you control the lights by either the P or the R, but not both. And this is an XOR gate. So either the R will control it, and this will be 1, or the P will control the light. Other than this, it's going to be 0. In the mode 1, the podium will control it. So whenever the podium is 1, the output will be 1. So the podium switch now is in control. And in mode 2, the rear switch is in control. So whenever the rear is 1, the output is going to be 1. We can get the function of each one of these modes. We know that this is an XOR, which is also the equivalent of P bar R or P R bar. The function here is the light H will be equal to P, which is this one. So you can see the resemblance between the P and the output. Similarly for M2, it's going to be R. Now, to draw the block diagram, we know that we can define those 4 I's, or capital I's, which we define here. It's called mode control signals. and we choose the I in the diagram to be 0, 1, 2, and 3. So you can see that this is I0, I1, I2, and I3. And you can simply get all the min terms here after those ends by applying the input P and R. For example, the first min term will be P bar and R bar. So this is going to be the first min term. And we will end it with the mode I0. This way, we generate P bar, R bar, and I0. We can do a similar thing over here. We will generate P bar, R, I1, and we will generate P, R1, I2 here, and we will generate P, R, I3 over here. And if H is as follows, then we will OR those 4 together to get H. Now what we did here is, since we are not going to use I0, the only control signals considered is I1, I2, and I3. And the reason behind this is, if you go back to this truth table that we described earlier, you can see that in the outputs H, we have zeros in all of the modes, M0, M1, and M2, when it is 0 and 0. So we are not gonna use this one. It's always going to be 0. But for the other cases, there will be a 1 somewhere. Here we have 2 1s here, we have 2 1s here, and we have 2 1s here. And by applying what we just mentioned, the value of fixing, we can fix this to be 0. And we will do this in the block diagram by having a 0 here. And since M0 now, the remaining output bit is 1 1 0, 1 for I1 and 1 for I2 and 0 for I3, we would say that we will consider I1 here, we will consider I1 here, and I2 here, and I3 over here. So if you want mode 0, you will simply put 1 1 0, and you will get the corresponding H. If you want M1, you will simply put 0 1 1, and if you want the last mode, you will put 1 0 1, and you will get its corresponding function. So after this discussion, in the coming slide, we will formulate this idea to make it easy to manage. We will talk here about the enabling functions, because you will see it in many of the coming slides. Enabling permits an input signal to pass through to an output. Disabling, on the other hand, blocks an input signal from passing through an output, replacing it with a fixed value. The value on the output, when it is disabled, can be high impedance, as we discussed in the tri-state buffers. So, for example, here, you can have this AND gate. The X will pass through to the F if the enable is equal to 1. If it is equal to 0, then X will be blocked. So when disabled, you will have 0 output. You can do the opposite if you put an inverter here. Now, when it is disabled, the output is having the value 1 because you are using an OR gate. So if you want to disable it, you will get 0 here. And because of that, after the inversion, you will have 1. And this one, no matter what's the input, you will have 1 at the output. This is the usage of the enables. You can see it in another way. Here, the enable, it could be 0 or it could be 1. If it is 0, then the output is going to be 0 regardless of the value of x. If it is 1, then the output will be whatever value of x. In the other design where you have an inverter and OR, now you will, if you have in the enable the value 0, after the inverter you will have it as 1. And because of this, regardless of the value of x, the output will be always 1. If you take the other input when the enable is 1, then after the inverter it will be 0, and the result will depend on the value of x, and now the x can pass to the output. Now we will discuss the first major component of this chapter, which is decoding. We have 4 major parts that we are going to discuss: decoding, encoding, selecting or multiplexing, and demultiplexing. The first one being the decoder. The idea of the decoding is the idea of the conversion of an m-bit input code to an m-bit output code, where m is between n and 2 to the power of n, such that each valid code word produce a unique, distinguished output code. The circuit that perform decoding are usually called decoders. They are called M-to-M decoders, or simply N colon M, and we say it N-to-N line decoders. And this M, as we said, is less than 2 to the power of n. It can generate 2 to the power, this is the upper bound. The upper bound is 2 to the power of n, or fewer minterms of the n input value. So if we consider m to be the upper bound, which is equal to 2 to the power of n, the decoder is called n to 2 to the power of n decoder. As you can see here in the block diagram, we have n bits as inputs, denoted from A0 to AN-1, and we choose the letter A because it's usually tied to certain adders. And we have m elements in the outputs, starting from D0 to DM-1, and we choose the letter D because it's usually tied to a certain data. And this decoder is kind of converting from an N input to M output. These Ds are less than or equal to 2 to the power of n. And the name of the decoder, usually we write it inside the box of the decoder here, N to M line decoder, or we write it as N colon M. As examples, so you understand the idea better, this is a 1 to 2 line decoder, which is the simplest. Here we have only one input, which is A0. It could be 0 or 1. And we have two line outputs, which is D0 and D1. So we have this input A, and we have two outputs, D0 and D1. We could consider it either A or A0. It's fine. To get the output D0 and D1, it's the idea is very simple. D0 will be corresponding to the first min-term, and D1 will be tied to the second min-term. The first min-term will be A bar, and the second min-term is going to be A. So we call it, or we get the equation of the outputs D0 and D1 by knowing the min-terms that we studied before. Since we have only one variable, the min-term here is D0 is equal to A bar, and the min-term for D1 is equal to A. In a truth table, that will be, the D0 will be the inversion of the A0, as you can see, and D1 is going to be A. This is the simplest decoder, which is 1 to 2 line decoder. If we have 2 to 4 line decoder, notice the relation between the input and the output. If we have 1, then the output is going to be 2 to the power of 1, which is equal to 2. If we have the inputs to be 2, then the output is going 2 to the power of 2, which is 4. Now, similar idea here. We want to generate the min-terms for each one of them. The D0 here is going to correspond to A0 bar, A1 bar, as you can see here. The D1 is for A0, A1 bar. The D2 is for A0 bar, A1, and the D3 is for A0 and A1. And now the idea of decoding is showing up. If the address having the first min-term 0, 0, being A0 bar, A1 bar, the output will be in D0, which is this output, only you have the output 1, and the rest, they will have 0. It's like the name suggested, it's decoding the address. So if the address here is 0, 0, you light up this first output by choosing the value here to be 1, and the others will be 0. If you choose 0 and 1 as the address, so it will be 0 and 1 here. It will be 1 in A0 and 0 in A1. This way, you will generate 1 in D1 and zeros in the 3 other data lines or the output lines. So you can see that it's giving you 0, 1, 0, 0. Similarly for 0 and 1, if you have this value 0 and 1, then you will choose 1 to be here, and the other data line is 0. The last one, if it is 1, 1, you will choose this one to be 1, and the 3 here is going to be 0. You can also understand this in decimal. If you choose this to be 0, 0, then the value here is corresponding to the decimal number 0. Here it's the decimal number 1, here it's the decimal number 2, and here is the decimal number 3. So if you want the decimal number 2 to be the input, this will generate the output of D2 to be 1 and the rest to be 0. So as you can see, there is a relation between this decimal number and the data line D2, and so on. To draw the block diagram, we generate the minterms simply by having 4 different lines, 2 for A0, when one line is the normal A0, and one line is the A0 after inversion. Similarly for A1, a line after the inversion, and the line where is you having A1 in a normal way. And then you will get the 2 bars first here, and then one of the lines will be bar for this and the other is not. Here you have the bar here from A1, and you have the normal one from A0. In the other end, you will have the other way around. You will have the bar from A0, and you will have A1 normally. And the last two, you will have it normal values, which is A0 and A1, to generate the third data line. Now, the 2 to 4 line decoder is actually made up of 2 1 to 2 line decoders and 4 AND gates. So as you can see, if this is the 1 to 2 line decoder, you can see this decoder here with this line. Similarly, you can see it for A1 here with this line. Of course, there are certain branching. So you have 2 1 to 2 decoders in the design of the 2 to 4 line decoders. And in addition, since you have 4 different outputs, you will have 4 preceding ANDs, preceding the data lines. So now we will discuss this idea, which is called the decoder expansion. The general procedure given in your book for any decoder with n input and 2 to the n output. This procedure builds up a decoder backward from the output. You start from the output and go to the input. The output and gates are driven by 2 decoder with their number of inputs either equal or differing by 1 bit. These decoders are then designed using the same procedure until 2 to 1 line decoders are reached. And this procedure, the procedure can be modified to decoder with the number of output that are not equal to the upper bound, which is 2 to the power of n. This procedure is detailed on the book, but here we will give you some of the decoder expansions and how you manage it in an easier way. So let's have this example, which is a 3 to 8 line decoder. Now, the number of outputs are 8. And since we have 8 outputs, we will have 8 ANDs. Also, the number of inputs to the decoders driving the outputs ANDs is going to be 3. So simply the number of inputs are 3 and the number of outputs are 8. The closest possible split is you will have 2 to 4 line decoder, and also you will have 1 to 2 line decoder. And to see this split and how is it matching the 3 to 8 line decoder, You can add those numbers. 1 plus 2 is equal to 3. And you multiply the outputs. 2 times 4 is equal to 8. So that's one of the possible splits. Now, the 2 to 4 line decoder, this one, now we are going in a nested tree. We will apply the same rule that we are applying to the 3 to 8 to the 2 to 4 line decoder. The number of outputs here are 4, which will be the number of ANDs as well. And the number of inputs are 2. And we could build the 2 to 4 line decoder, as we explained in a previous slide, using 2 1 to 2 line decoders. We can also apply the same thing that we said. Since there are 2 versions of them, we will write the other version. You can add 1 plus 1 is equal to 2, and 2 times 2 is equal to 4, just for confirming. And we can see in the next slide the resulting block diagram. You can see that what we wanted is 3 to 8 line decoders. So the data start from D0 to D7. The outputs from D0 to D7, and the inputs is from A0 to A2. And you can see the minterms for D0. It's like the index of the minterm. A0 bar, A1 bar, and A2 bar. Similarly for D1, A0, A1 bar, A2 bar. For the 2, let's take an example. For example, the 5. We know the 5 in binary is like this. So it's going to be A0, A1 bar, and A2, and so on. Now, since we know now the inputs and the outputs, certainly before every output line, you will have an AND. And because of this, you will have 8 different ANDs. Now, to do the decoder expansion, we said for the 3 to 8 decoder, we will use 1 2 to 4 line decoder and another 1 to 2 line decoder. This decoder will generate 4 outputs and will have 2 of the inputs. The other one will have 1 input and 2 outputs. In any decoder, the number of outputs, if it is equal to the upper bound, if you have the inputs to be n, then the output will be 2 to the power of n. And as you can see here, we have 2 inputs. So for sure, we will have 4 outputs in the 2 to 4 line decoder. If you see it, if you want to see it in the full decoder, then if you have 3 inputs here, then you will have 8, which is 2 to the power of 3 lines in the outputs. Of course, you will have these connections to get the respective minterms by doing the following. We know that the 2 to 4 line decoder, each one of the outputs have its own corresponding minterms. Given that we have only 2 inputs, the first minterm will be A0 bar, A1 bar, and then you will continue until you reach to A0, A1, corresponding to the minterm M3. For a 1 to line decoder, you will have only 2 simple minterms, A2 bar and A2. To generate the minterms for the 3 to 8 decoder from this one, you will copy this one 2 times. You will copy it first here, and then you will copy it again here. Now, for the last one, and because of this copying, you can see that the branching here is doing this way. You will have one going to this end, and the other one goes to the and corresponding to D4. Similarly, for example, for D2, you will have one here in D2, and you'll have the other one in D6. The 1 to 2 line decoder outputs will be split into 2. The A2 bar will go here to the first group, and the A2 will go to the second group. Now, if you want to check the design of the 2 to 4 decoder and the 1 to 2 line decoder, you can zoom in inside them and you find them to be like this. You have 4 2 input ANDs with 2 of the 1 to 2 line decoders, as we explained earlier, and you will have this one to be a simple line with an inverter. And you can see the behavior of the decoder expansion. You will have inverters, group of ANDs, and another group of ANDs. And if you have more expansions, you will have more group of ANDs. Similarly, here you have inverter and so on. So to generalize this idea, the rule for building larger decoders could be, if you have k to 2 to the power of k decoder, you will need 2 to the power of k output AND gates, which is tied to the output. Now you check the input. If k, which are the input lines, can be divided by 2, meaning an even number, then you can use 2 versions of a smaller decoder. This small decoder will be the division of k and the division of this k in the power. So k divided by 2 to 2 to the power k divided by 2 decoders. So you will have 2 of them. Now, if k is odd, then you will have 2 decoders. The first one will have k minus 1 divided by 2, as you can see here. This is in the input, and this is in the output line. And the other one will have k plus 1 divided by 2 here and in the power line. Usually, what the split that you will have many small decoders and you will have few big decoders. As examples, if you remember the 2 to 4 decoder, now k is even here. So you will need 4 output AND gates. And since 2 is even, you will use 2 versions of 1 to 2 decoder. While the 3 to 8 decoder, since k now is equal to 3, you will need 8 output AND gates, which is 2 to the power of 3. 2 to the power of 3, which is equal to 8. And since 3 is an odd number, you will have different decoders like this. You will have 2 versions of 1 to 2 decoder and 1 of 2 to 4 decoders. I think this is not correct. This is supposed to be 1, since in the previous one here, we have only 1 to 2 decoder, and we have 1 2 to 4 line decoder. Now, if you want to see how many 1 to 2 line decoder inside this one, then yes, they are 2. Now, how to build a bigger decoder? Let's say that we want to build 4 to 16 line decoder. Let's get rid of the animation to make it clear for you. If you have 4 to 16 line decoder, you will have 4 inputs, which is A0, A1, A2, and A3, and 16 outputs, D0 up to D50. This is shown here. You have A0, A1, A2, and A3, and the outputs from D0 to D15 shown like this. And because you have 16 outputs from D0 to D15, you will have 16 AND gates. I defined them in 4 groups, and I draw the first group and also the last group. And also I drawn the first AND of the second group. I don't have enough space in this slide to list all of the ANDs. We will use here, since 4 is an even number, which is this input, we will use 2 to 4 decoder. This is the first one, and this is the second one. The first 2 to 4 decoder will have A0 and A1, and will give you the 4 output D0 to D3, and I denoted the minterms for each one of them. Now, the second 2 to 4 decoder will have the input A2 and A3, and it will have the denoted minterms. Now, to mix them to generate the outputs of the 16 outputs, since you have only 4 outputs here and 4 outputs here, you will copy this one into the first group. You will also copy it here, and you will copy it here, it's not shown, and you will copy it also in the last one. Now for this one, you will kind of distributing this way. You will get the first one in the first group. You will get the second one in the second group, the third one into the third group, and the last one in the last group. And this way you generated all of the minterms. Now, for a 5 to 32 line decoder, let's also get rid of this animation to make it easier to understand. You will have 5 inputs here from A0 to A4. And you will have 32 outputs from D0 to D31. Since you have 32 outputs, you will have 32 ANDs. Each one of these ANDs is 2 inputs. And since 5 is an odd number, one of the splits, it could be 3 to 8 decoder and 2 to 4 decoder. You can also check by adding 2 plus 3 is equal to 5. And you multiply 4 times 8 is equal to 32. And you do the same thing. The only difference between the previous slide and this slide is that you have a 3 to 8 decoder instead of the over here, instead of the 2 to 4 that you had in the previous slide. And because you have 3 to 8, you will have 8 different minterms here, starting from A0 bar, A1 bar, A2 bar, up to A0, A1, and A2. And you will copy this group 4 times like this. This is the first one. I actually showed only 5 of them. There are 3 more. And then you will copy it again for another 8, copy it again for another 8, and you will copy it here for another 8 times. So this 8 minterms will be copied 4 times this way. And then you will distribute these. This one will be in the first group, and this one will be in the second group. This one will be in the third group, and this one will be in the last group. Please notice that there are supposed to be 8 here, but I only showed 5. They are also supposed to be 8 in this region, and I only showed 4 of them. Also, the missing parts here, you can continue it if you have a bigger or space. And there will be 8 and 8 different minterms. You can see that if you have 8 minterms here, 8 another minterms here, 8 another minterms here, and 8 times 4 is 32, which is matching the output of the 5 to 32 line decoder. Now, suppose you were asked to do the expansion for 7 to 128 line decoder. So you would say that I have 7 inputs from A0 to A6. I have 128 outputs from D0 to D127. You will have 128 output AND gates, which is matching the output. And you will use 4 to 16 and 3 to 8 decoders. 4 to 16 line decoder, we already show you how to build it. And the 3 to 8 line decoder, we also showed you how to build it. The 4 to 16 line decoder will have 4 inputs and 16 outputs and 16 AND gates, and it will use inside it 2 to 4 decoder. The 3 to 8 line decoder having 3 inputs, 8 outputs, 8 AND gates, and it will use 2 versions of 1 to 2 decoder and 1 of the 2 to 4 decoder. This is more examples. You could build a 4 to 16 decoder using 5 2 to 4 decoders. You can also design the same thing using 2 3 to 8 decoder. You can design the 4 to 16. It's the same on all of the 3 versions using 1 3 to 8 decoder, 2 2 to 4 decoder, and 2 AND gates. You design 5 to 30 to 32 decoder using, you can use the design it using 2 4 to 16 decoders. You can also design the 5 to 32 decoder using 4 3 to 8 decoders and 1 2 to 4 decoders. You can also design the 4 to 12 decoder using 3 to 8 decoder, 2 to 4 decoder, and some AND gates. And I will leave this as a challenge for you to try to design them and get the block, the corresponding block diagram. Now we discussed the idea of the decoder. We will add an enable line to the decoder. If, for example, we have 2 to 4 decoder and we wanted to add an enable line, this will be the equivalence of adding another 4 AND gates before the outputs. Those AND gates will be tied to the enable this way. So if the enable is equal to 1, it will pass the previous outputs to the data lines. If it's 0, then it won't pass it, and the results that's going to be shown in the output is going to be 0 0 0 and 0. To show you the same idea in the truth table, if the enable is 0, regardless of what's the address or the inputs in the address lines A0 and A1, the output D0 to D3 will be 0 0 0 0. If it is 1, if the enable is 1, then the decoder will work normal. If you have this min term, this one will be 1 and the others will be 0. If you have this one will be 1. If you have this one will be 1. And the last one, the output D3 will be 1 and the rest will be 0. So that's the tax that you are going to pay. If you add the enable, you will need to have 4 more AND gates. The same thing that we just described is written here. Generally, you attach an M enabling circuit to the outputs. You can see it through the truth table, and you can see the don't care that denotes both 0 and 1 is okay, and we don't, it means that it's a don't care. The combination containing 2 of the don't care represent 4 binary combinations, which is 0, 0, 0, 1, and 1, 1, 1, 0. All those 4 combinations here, regardless of their value, if the enable is 0, the value of the output is going to be 0. In an alternative way, it can be viewed as distributing the value of the signal enable to 4 outputs. In this case, it would be called a demultiplexer. The same idea here, you can switch those 2 to this position and switch the enable over here. And if you make this switch, it would be called a demultiplexer. And we will show this in a future slide. Notice that this is the regular decoder. And this one here is the extra set of the AND gates. The idea of the demultiplexer that we mentioned here is shown in this slide. The decoder with enable and demultiplexer relation. The decoder with the enable as inputs can be viewed as distributing the value of a single enable to 4 different outputs. And in this case, as we said, we will call this a demultiplexer. So this is the decoder with the enable. If you want to generate the demultiplexer, it would be like this. You can see that this demux have the enable. The enable now is here. And these 2 lines, the address lines will be here. Now the naming will be different. This would be the input. And this would be the selectors. But we will show this in more details when we talk about the multiplexer and the demultiplexers later. After we describe the decoder idea for you, now we will show the decoder-based combinational circuits using decoders and OR gates. This is referred to as a structure implementation method, since a specific underlying structure is assumed in each case. Any function we want to implement M functions out of N variables. We used this, or we did that with sum of min term expression, and we use it with 1 to n to 2 to n line decoder and m number of OR gates for each output. So if you want to design any combinational circuit, you could either use the old design methods that we described in a previous video, or you could use a decoder to do that. To use the decoder, you have to use OR gates with it. So to do that, you will have sum of min term expressions, and then you will use 1 decoder with a specific size, n to 2 to the power of n line, and you will use m number of OR gates based on how many functions you have. If you have m functions, you will have m different OR gates. There are 2 approaches. The approach number 1, you find the truth table for the function, and then you make a connection to the corresponding OR from the corresponding decoder output whenever a 1 appears in the truth table. The second approach, you find the min-term for each output function, and then you OR the min-term together. It's very close to each other. We will show you this in an example. If you were asked to design and implement a majority function, which is this having three inputs, A, B, and C. And you were asked to design it using a 3 to 8 decoder. Even if it wasn't mentioned to you, since you know that you have 3 inputs, the perfect decoder for you is 3 to 8 line decoder. Now we know that the truth table, we could construct it for 3 variables this way. And since this function is called the majority function, it's like a voting function, where if the number of ones, you count the number of ones against the number of zeros in every row. So here, the 0 win, here, the 0 win, here, the 0 win, here, the 1, the number of ones we have here is 2, the number of zeros only 1, so the 1s win. Here, the 0 win, and the last 3, the 1 win. This is the majority voting function, or simply majority function. Now, to design this using the decoder, you simply draw the 3 to 8 line decoder this way. It has 3 inputs, A, B, and C, and you have to mention the position of the input. You can see that the C here is the least significant. We denote it with this 0, and this one is the most significant, which is this one. We denote it by 2. We have 0, 1, 2, since we have 3 inputs. And we will have the outputs starting from 0 to 7. We know that each one of the outputs is corresponding to one of the min-terms. And since we know that any function could be implemented by collecting its min-terms, you get its min-terms and then you OR them together. The min-terms are already there. This is 3, 5, 6, and 7. So this is the 3, 5, 6, and 7 already in the output of the decoder. You just need to OR them. So we will do it by the first approach. You know the min-terms are 3, 5, 6, and 7. So you will collect those and add them in a 4-input or gate to get the function f. And you can see how simple is this using 3 to 8 line decoder. As I said, this indicates the most significant and the least significant bits. And this is tied to the position in the truth table. This is another example. This example shows to you this function. It's a 1-bit binary full adder, and you were asked to design and implement a 1-bit binary full adder using decoders. We will discuss the idea of the adders in the video next to this one when we talk about arithmetic. But for now, we will consider S, which is the sum, to be the function, the sum of min-term 1, 2, 4, and 7. And the carry, C, is the sum of the min-terms 3, 5, 6, and 7. If this were given to you in the question, you can construct the truth table by having the A, B, and C as inputs. Now C is the least significant, the A is the most significant bit. This is why in the input of the decoder, you will put C here and you will put A right here. Now the min-terms 1, 2, 4, and 7 for the sum is here. This is 1, 2, 4, and 7. the minterms for the carry 3, 5, 6, and 7. 3, 5, 6, and 7. Now what you do is, because you have two different Boolean functions, you will have two different ORs. And you collect their corresponding minterms as inputs for this OR. For the sum, it was 1, 2, 4, and 7. So you get 1, 2, 4, and also 7. For the carry, it was 3, 5, 6, and 7. So you get 3, 5, 6, and 7. You can see how easy is this, to the point that you could construct the 3 to 8 line decoder 1-bit binary full adder directly from the functions. So if you have the sum and the carry, you know they are 2, so you will have 2 OR gates, and then you get the 1, 2, 4, 7. We have 1, 2, 4, 7. Similarly, for the carry 3, 5, 6, 7, you will get 3, 5, 6, and 7, and that's it. The choice of the 3 to 8 line decoder is based on the number of inputs that you have. You had 3 inputs, so it will be 3, 2, 2 to the power of 3, which is 8 line decoder. This is another exercise. If you were asked to design and implement the function if with 2 inputs, A and B, using a 2 to 4 decoder with an enable input and an OR gate, you have this function. This was given to you, and you were asked to design it. You could consider the C as an enable, and you will write it here. And notice that it must be factored. It must be factored. Even if the function is not factored, you have to generate the enable, which is in this case the C, as a factored input, and you put it right here. And the other two here are certain minterms in the 2 to 4 decoder. The first minterm here, which is AB, correspond to number 3, and A bar, B bar correspond to number 0. Since you know these, you OR them together to get the function. Get the function F. If you were asked to design the same function, but you were asked at the end to use a NOR gate, you could do this by getting the remaining minterm. So previously, we added the 0 and the 3 to the OR gate. Now you will take the remaining ones and you add them to a NOR gate to get the function F. And the idea behind this is the complement of a function, and we described this in a previous video. Now, if you were to ask to design and implement the function, it's the same function that we said before, but you use only 2 to 4 decoder with 2 tri-state buffer. You could do that as follows. You will have the decoder like this, and you have to get the C or distribute it to both of the terms. So you'll get A, B, C, or A bar, B bar, C. Now notice that you no longer have the enable in the decoder. If you don't have the enable, you can force the enable by using the tri-state buffer like that. So you will connect the B bar C and the BC. For example, here we have the B bar C and we have the BC, and we choose the A to be the selector of the tri-state buffers. It's either going to be this one or this one. If you want to generate A bar, B bar, C right here, then you will take B bar C and you will have A bar right here after the inverter. If you want this one, ABC, then you have BC, and after that, after the inverter, it will be ABC, since you have the A going to this tri-state buffer, and this way you generate the function. If you compare this to the previous two slides, you will notice that you don't have enable anymore, and you are forcing the enable using the idea of the tri-state buffer. Notice here that we used A as the enable. We could use C as the enable, and it will be correct as well, but you need to choose the right minterms. As another exercise, if you were asked to design and implement the functions F2, F3, and F4 using a 3 to 8 decoder, we already know the drill and what to do. But here we will give you certain ideas that will make your design simpler and won't have a lot of inputs, especially when you are picking the OR gates. So you notice that here you have F2 as 0, 2, 3, 5, 6, and 7. F2, this F2 were given to you. Also, the F3 is given to you, and the F4 is also given to you. Was given to you the same as you can see. So, F2 have 0, 2, 3, 5, 6, and 7. We know that if we get the complement of F2, you will have only 2 minterms, because it's 3 variable and already you have 6 minterms here. So if you took the complement, it will have only 2 minterms. And those 2 minterms is corresponding to A bar, B bar, C, or A, B bar, C bar, because you have 1 and 4. Just to remind you, the 4 is 0, 0, 1, and this is 0, C bar, B bar, and A, C bar, B bar, and A. So if that's F2 bar, then F2 will be, you will take this function and you will put a bar on top of the whole thing. The idea here is that the OR with the inverter, it will be an OR gate with 2 minterms, M1 and M4. And this is what we are going to do in the block diagram. F3, if you were given A, B bar or B, C, you notice here that we have 3 inputs, and these are not minterms. You don't know exactly which minterms right away. So to do this, we use simple Boolean algebra. We added the missing C and the missing A this way, and then we distribute the A, B bar to the C and the C bar, similarly here to the A. And now you know that this is M5, M4, M7, and M3, and you reorder them like this. There are 4 minterms. If you were thinking that you will get the inversion, you will end up with also 4 minterms. So it doesn't make a difference for you, and you stop right here. For F4, you have A or B or C bar. And you notice that you are missing many variables. You're missing 2 variables here, 2 variables here, and 2 variables here. If you try to do the same thing that you did in F3, it will be a long process. A smart idea is to get the F4 bar, and you know that the complement of this max term is this min term. You flip everything. Or you apply De Morgan law. By applying De Morgan law, you will break the line and change the sign. The A will be A bar, the R will be and, the B will be B bar, and the C bar will be C. And you know that this is M1. If you want to get F4, then it's going to be M1 bar, which is also the equivalent of the other missing midterms, which is M0, M2, M3, M4, M5, and M6, and also M7. But in a smart idea to get the short version of every function, you will implement F2 this way. You will implement F3 this way. And you will implement F4 this way, because this is the short way. Notice that F2 will have the two minterms shown here, which is 1 and 4, but there will be the input of a NOR gate. F3 is normal. You get the minterms 3, 4, 5, and 7, and you OR them together. F4, you will get M1 and you will invert it using a single inverter. And we will do this in the next slide like this. Here's F2, NOR gate with M1 and M4. F3 is normal. You get the 3, 4, 5, and 7. And the F4 have a single inverter of M1. So the idea here, the usual case is you are using OR gates in all the functions. If you have 3 functions, you will have 4 OR gates. However, sometimes it's a smart idea to use the complements and you manipulate the minterms to get a smaller gates. Here we have only an inverter and an OR gate. Now we will discuss the other idea, the second core idea of this talk, which is the encoding. The encoding is close to decoding. There is a relationship between the encoding and decoding. Actually, the encoding is the opposite of decoding, which is the conversion from an M-bit input code to M-bit output code, where M is between N and 2 to the power of N. Again, the upper bound here for M, which is the input right now, is 2 to the power of N, such that each valid code word produce a unique output. The circuit that do that is called an encoder, and an encoder has 2 to the power of N or fewer input lines and N output lines, which generate the binary code corresponding to the input value. Typically, an encoder converts a code containing exactly 1 bit, that is 1, to a binary code corresponding to the position, the correct position in which that 1 is appearing. To explain this further, this is the encoder. It has M Ds from D0 to M-1. Usually it's either equal to the upper bound 2 to the power of N or less than that. And you have output bit from A0 to AN-1. Any encoder circuit, the data line is much more than the address line, or in another way, the inputs are much more than the outputs. You can see that if you go to this direction from M to N, you are doing encoding. If you go to the opposite direction, it will be decoding. It will be decoding. And we mentioned this before, that a decoder, N to M decoder, have N input or address lines and M output or data lines. Now you see the relation between the encoding and decoding is actually the opposite. The encoder performs the opposite of operation of the decoder. And that's why if you connect both of them together, if you have a decoder generating D data line, the encoder will accept these data line as inputs and it will generate the original inputs as outputs over here after the encoder. This is only for educational purposes to show the relationship between the decoder or the encoder. If you connect this really in real world, you have a chip and another chip and you connect them together, you are not making any progress. Whatever you have in the input is generated at the output. So it's equivalent to just a simple line. As an encoder example, if you were asked to do an octal to binary encoder, the inputs will be 8 bits corresponding to decimal digits from 0 to 7, from D0 to D7. So these are the inputs you have from D0 to D7. Should be 4, 5, 6, and 7. So you have the inputs from D0 to D7. And you have 3 outputs, which is the 3 bits with the binary code. What you want, if you have D0 equal to 1 and the rest are 0, then the generated code, you want it to be 0, 0, 0. If, for example, the 1 was corresponding to D4 and the rest are 0, this means that you want the code, the generated code word to be 4, which is 0, 0, 1, and so on. So the function, if the input bit D of I is equal to 1, then the output A0, A1, A2, this output is the binary code for the I. As in equations, if you want to get the function, if you try to use Karnaugh map, it's going to be super difficult for you. And the reason is because you have 8 inputs. And you know, we explained to you the Karnaugh maps up to 4 inputs on. So luckily, we have only a single one in each row in this table. And because of this, now A2, if you want to get it, you will look at the ones, and you will see that the first one corresponding to D4, this one corresponds to D5, and this one corresponds to D6, and this one corresponds to D7. You write the equation this way. This is easy because the inputs of the encoder having a single one in each row. Similarly, for A1, you have those 4 ones. And they are going to be D2, D3, D6, and D7. Similar idea for A0. Now we will check another encoder example. This example is a decimal to BCD encoder. And the inputs here are the 10 bits corresponding to the decimal digits from 0 through 9. So you have D0, D1, D2 up to D9. And you can see it here in this keypad. Suppose you have keys for 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you press, for example, the button 0, it will generate for you 1 here and zeros everywhere else.
And similarly for the other buttons. The output, you want to generate a 4 bits with their binary value. The binary value, for example, corresponding to 0 will be 0000. The binary value for 9 will be 1001. So the function is, if the input bit d of I is 1, then the output will be the binary representation of di as 4 digits, A0, A1, A2, and A3. And that will be the BCD code for the I. The truth table could be formed, but alternatively, the equation for each of the 4 outputs can be obtained directly if we know that the input d of I is a term in the equation a of j if the bit aj is 1 in the binary value for I. So you will see A3, which is the most significant bit, only in the binary code number 8 and number 9, since the 8 is 0001 and the 9 is 1001. And so you can see that the A3 will generate only in 8 and 9. So A3 will be equal to D8 or D9. For the least significant bit, for example, A0, you will see it only on the odd binary code, D1, 3, 5, 7, and 9. You can also generate it for A1 and A2 in a similar way. Now, to get the block diagram for this encoder example, you simply use an encoder. The encoder will receive the Ds from D0 to D9, and it will generate 4-bit binary code for you. This is actually the definition of the encoder. Notice that this encoder will be 16 to 4. But we are using only from 0 to 9, since the other code are not included in BCD. Now, if you were to, if you said that I noticed that we have common terms, D6 or D7, and could be extracted from A2 and A1, and maybe I'll have some cost reduction, then the answer is no, because we already used a previously designed encoder. Now we will see the idea of priority encoder. If more than one input value is 1, you can see that in all the previous encoders and also decoders, we have only 1 bit that is equal to 1. In the encoder case, if you have more than 1 input value that is equal to 1, then the encoder designed previously doesn't work. One encoder that can accept all possible combination of input values and produce a meaningful result is the priority encoder. So priority encoder will accept some inputs will have more than 1. More than a single logic 1. Among the ones that appears, it selects the most significant input position and would say that this is the highest priority. Alternatively, you could think about the least significant as well. That was containing a 1 and respond with the corresponding binary code for that position. to explain this, you have this example, a priority encoder with 4 input from D0 to D3. The highest priority to the most significant one. And the code output, we have A0 and A1. This is A0 and A1. And you have the output V, where V indicates there is at least one or a single logic one present in the input code. This table shows you how the priority is working. And you can see in the first row here, you have the input 0, 0, 0, 0. The output will be no code, which is don't care, because you don't have any one in the inputs. There is no logic one presented here. So the V will be 0. The other codes, you have one somewhere. This is why V is equal to 1. Now, if you have 1 in position D0, then the code is 0, 0. Now, if you have 1 in the position D1, regardless of what's the value here, whether it's 0 or 1, then the output would be the code 1, 0. Notice that we start using the don't care in the inputs. And because of this, this row is actually corresponding to 2 minterms. The first one is 0, 1, 0, 0, and the second one is 1, 1, 0, 0. Now here we have 2 don't cares, and we have 4 different codes, and the last one we have 3 don't cares, and we have 8 corresponding minterms. So if you you expand those rows, you will start from 0, 0, 0, 0, and you will end up with 1, 1, 1, 1, which will have 16 full rows. Now, to continue the operation of the encoder, if you have 1 in this position, regardless of this value, the code will be 1, 0. If you have 1 in this position, now it has the highest priority, and regardless of the less priority bit positions, the code will be 0, 1. If you have 1 here, then the code will be 1, 1, regardless of those 3 positions. So the X is in the input part of the table represents 0 or 1 because it's a don't care. It could be either 0 or 1. Thus, the table entry corresponding to product terms instead of min terms. The columns on the left, this shows that all the 16 min terms are presented in this table. Now, what to use if you have 4 inputs and you want to generate 2 outputs with V? You would use a priority encoder. You would use a priority encoder. Now, you could use the K-map to get the equation, but this could be read directly also from the table. If you want to use the K-map, for example, for A1, let's say, you can say that A1 here, it has don't care in the first position, which is 0, 0, 0, 0. So it has don't care here. And it has 0, 0 in the next 3 minterms. 1 minterm here and 2 minterms here. So it has 0, 0, and 0. And the rest is 1 and 1, meaning 1 in the next 4 minterms and 1 in the next 8 minterms. So 1 in the next 4 min terms, 1, 1, and 1, and 1, and 1s in the next 8 min terms, 1, 1, 1, and 1, 1, 1, 1, and 1. And you can minimize it this way. This will be corresponding to D2, and this one will be corresponding to D3. You can easily read this from the table. From the table, this table directly, by saying A1 here, it has 1 over here and 1 over here, and this one corresponds to D2, and this one corresponds to D3. D2 and D3. And of course, you could use also the K-map to generate those two functions. Now, you could use the idea of the priority encoder in this example, but now in an opposite way. Instead of having the inputs directly, D0, D1, D2, and D3, you will have them inverted. You can see the bubbles here. So the priority encoder with the 4 inputs, now they are D0 bar, D1 bar, D2 bar, and D3 bar. The highest priority to the most significant one, and also the same outputs that we had before. Now here, if there is no 0, not a single 0, now we are looking at the 0. If there is no zeros, then the output would be the output V would be 0, and the inputs A0 and A1 will be don't care. So that doesn't have any value here, doesn't have any code, because no zeros at all. Now, with the same idea that we described before, but now we are looking at 0. So this 0 will have the code 0, 0. This 0 will have the priority, and the code will be 1, 0. This 0 will have the code 0, 1, and this 0 will have the code 1, 1. And in a similar way, you can get the equation of A1, A0, and V. But now you have the don't care in position number 15. For example, if you look at A1, you have the truth table upside down. So you'll have the zeros at the end, 0, 0, 0, 0, and you'll have 1, 1, 1, 1 at the beginning. So you have don't care at position 15 in the Carnot map. And then the next 3 min terms going back will be 0, 0, and 0. This is why we have don't care here and 0, 0, 0 going back, and the rest will be 1, and you will find out that the A1 is D2 bar or D3 bar. After that, we will go to the priority encoder example. Now, what if we have 5 inputs? Now, we cannot use the Carnot map anymore. If we have a 5 input like this, and we consider the same idea, we have starting from 0, 0, 0, 0, 0, up to 1, 1, 1, 1, 1. There will be 32 different rows, but some of the rows are combined because of the presence of the don't care. Since we have only 1 don't care, you will have 2 rows combined together in a single row. Since you have 2 don't cares, you will have 4, 3, you will have 8, 4 don't cares, you'll have 60. Now, the code that you have will be, if there is no one at all, there is no code, and V will equal to 0. Other than that, you will have a valid code. This code will be 0, 0, 0 if there is a 1 here. There is a 1 here, it will be 1, 0, 0. 1 here, it would be 0, 1, 0. 1 here, which would be 1, 1, 0. And the 1 here will be 0, 0, 1. Now, to get the equation for the outputs V, A0, A1, and A2, you can get them clearly. For example, for the valid, you will get the ones here and you look at the table. Here you will have D0, since you have D0 here, 1, or D1, or D2, or D3, or D4. So it's fairly easy for the V. Notice that we have F1 and we define F1 to be D2 or D3. If you apply it here, it would be D0, D1, D2, 3, D2 or D3 or D4. Now, for example, for A2 here corresponds to D4. Now, for the other functions, A0 and A1, we have to be careful when we try to find the functions, because of the presence of zeros in the highest the data or highest input positions. So to get, for example, A1, you have 1 and 1 here. This one will correspond to D3, D4 bar, or D2, D3 bar, D4 bar. And you can take some factoring, which is the D4 bar, and you will end up with D2 or the D3. You can say that this is F1 and you also apply it here. For A0, you'll have this one here. For A0, I mean, you will have 2 ones. And this one would be D3, D4 bar. This one will be D1, D2 bar, D3 bar, D4 bar. And this way we get the function without the kernel map. Of course, you can apply some Boolean algebra to hopefully reduce the cost of the functions. Now we will move to the idea of selecting, but we will discuss this in the next video.